Hello everyone. This is Digital Power Application Support from NXP System Engineering Team. Welcome to this training. In this training, we will present our new bidirectional AC-DC reference solution. It can be used in applications where bidirectional power flow is required, such as onboard chargers for electrical vehicles and energy storage systems. Here is the agenda for this presentation. First, we will cover the overview of this solution. Then the AC to DC and DC to AC schemes will be introduced separately, including the basic operation principle and control strategies. In addition, we'll look into some key points in hardware and software design. And finally, the test results and waveforms related to this reference solution are presented. Let's start with the solution overview. This is the prototype being made, including 2 boards, a high-voltage power board, and a control daughter card. The NC56FA3783783 digital signal controller is used in this design. According to the energy flow, the bidirectional AC-DC converter can work in AC to DC or DC to AC mode. In both modes, the maximum output power is 800 watt under high line and 400 watt under low line. In the AC to DC mode, this design can accept the universal input from 85 volts to 265 volts, and the input frequency is 50 to 60 Hz. The output DC link voltage is 380 volts. The peak efficiency can achieve about 97% under high line and 95% under low line, and the power factor is always above 0.99. In the DC to AC mode, rated input voltage is 380 volts, and the output can be 220 volts 50 Hz or 110 volts 60 Hz, which can be manually configured or grid adaptive. The peak efficiency can achieve about 95.5% considering auxiliary power. The highlight of this reference design is that it supports 3 working modes: PFC mode, standalone inverter, and grid-connected inverter mode. Besides, it can switch smoothly between AC to DC and DC to AC mode. And in the DC to AC mode, standalone and grid-connected mode can also switch smoothly. Capacitor current feedback is adopted to suppress LCL resonance. PR controllers are used to eliminate the steady-state error and improve THD. Fast and stable DC bus pre-charging is implemented with triac and soft starting in AC to DC mode. And the light load mode is enabled for higher efficiency and power factor. Various protections for voltage, current, and frequency are enabled in this design. Free master support enables easy debugging and control of the system. And highly optimized library is used to help speed development and improve code execution efficiency. Here is the system block diagram of this design. This is a common full-bridge AC-DC converter consisting of 4 insulated gate bipolar transistor switches, followed by an LCL filter. The auxiliary power takes power from the AC or DC side, depending on whose voltage is higher. The NC56F83783 digital signal controller is used as the brain of this design. To handle the control of the system in all modes, multiple voltage and current components are sampled, including the DC bus voltage, inverter side current and voltage, grid side current and voltage, load side voltage, and the filter capacitor current. One UART port is employed to communicate with host computer for free master connection and firmware updating. And one UART and CAN port are reserved for communication with other modules, such as the subsequent DC-DC converter. There are also multiple LEDs on the board for status display. Now, let's take a look at the modulation schemes, control schemes, and some specific optimization strategies in different operation modes. First, let's look into the AC to DC mode. The function of the converter in AC to DC mode is to convert the AC input to a regulated DC voltage output while drawing sinusoidal input current in phase with the AC input voltage, which is what we often call the PFC function. When the controlled signal frequency is much lower than the resonant frequency of the LCL filter, the LCL filter produces the same frequency response as a single L filter with the same inductance in the low frequency band. On this basis, the working principle of the PFC converter based on an LCL filter works similar to that based on a single inductor filter. Looking at the circuit topology, it's a typical totem pole PFC. The switches on the left side operate at high frequency, while the switches on the right side are forward biased based on the input AC cycle. During the positive half cycle of the AC input, switch 2 acts as the main tube and switch 1 acts as the freewheeling tube to create the boost action. And the functions of switch 1 and switch 2 are exchanged in the negative half cycle of the AC input. Because IGBTs are used in this design, synchronous rectification has no efficiency advantage. The freewheeling tube and the low-frequency switches are turned off. The current flows through the anti-parallel diodes. Here, we see the control diagram of the PFC mode. It's designed based on the continuous conduction mode. The voltage outer loop regulates the bus voltage at the reference level and the inner average. Current loop ensures that the input current is in phase with the input voltage. Looking at the detailed implementation on the right side, the light blue box is the voltage loop, including soft start logic and a PI controller. In addition, DC bus voltage is also used as a compensation factor to improve the dynamic performance. The orange box is the average current loop. In the current reference calculation, input voltage feed-forward is adopted to eliminate the influence of input voltage fluctuation, and a software phase-locked loop guarantees the current reference track the input phase. In addition, to improve the control effect and system robustness, the final duty cycle not only depends on the calculation of the current loop, 2 extra compensations are also added. One is the theoretical duty cycle. The totem pole PFC in this design operates mostly in the continuous conduction mode, but it operates in the discrete conduction mode near the zero crossing of the input voltage, especially at light loads. The change in the converter dynamics will lead to input current distortion, so the theoretical duty cycle is added to simplify the current controller design for different operation modes. The other is the capacitor current feedback to dampen LCL resonance spike. Now, we will discuss some of the design details, starting with the pre-charging of the DC bus. Usually, a PFC converter requires a current limiting circuit to limit the pre-charge current. The most common method is to add a relay and a resistor. In this multi-mode converter design, controllable switches, TRIAC, are present between the grid and the converter as load and grid switches in DC to AC mode. In the PFC mode, the progressive phase control of the TRIAC can also serve the purpose of limiting the current in the pre-charging stage, so relay and resistor are not needed anymore. Looking at the waveform on the right side, the TRIAC is triggered in the second quarter of a positive half cycle, and the trigger point is increased cycle by cycle with a fixed step. Therefore, the DC bus voltage is charged to near the peak value of the input voltage step by step, and the charging current is limited by the step size. When it is determined that the bus voltage has reached close to the peak value of the input voltage, the pre-charging process ends and the TRIAC remains on. Here the method for light load efficiency and current quality optimization of this design is presented. When the light load condition is detected, the PWM drive signals are blocked periodically according to the output voltage peak value detection, which is equivalent to a reduction in the equivalent switching frequency. And when the PWM is on, the RMS value of the reference current is fixed. The transition logic between normal and light load modes is shown here. The software will automatically switch smoothly between the two modes based on multiple criteria including output voltage, voltage controller output, and output voltage change time. In addition, this multi-criteria mode switching is also very effective in suppressing DC bus voltage overshoot and drop. For example, in normal operation mode, if the DC bus voltage reaches a certain threshold, the PWM drive signals are directly turned off regardless of the current to enter the light load mode, which directly limits the maximum DC bus voltage. Next, let's take a look at the DC to AC mode. In this design, the two-level H-bridge inverter controls the power flow from the DC bus to the AC side, and it can operate in either grid-connected or standalone mode with seamless transition control. In order to facilitate peripheral configuration when switching modes, the same modulation mode is used in different modes in this design. The unipolar modulation is adopted. The switches on the left side operate at carrier frequency, while the switches on the right side are driven at the line frequency. Now, let's take a look at the controller selection. The PI controller is the most common and simple controller currently. Look at the baud diagram. The gain of the PI controller decreases dramatically with an increase in the frequency. So, the PI controller can't be used to track the periodical signals without error. In the DC to AC mode, whether it is the grid-connected current or the output voltage, the controlled object is the line frequency AC signal. To zeroize the error at the AC frequency, PR controller is a good choice. Looking at the baud plot, it's clear that the PR controller can provide large gain at a specific frequency. Besides, to ensure adaptability to the grid frequency, the quasi-PR controller is used in this design. Next, let's discuss the issue of inductor-capacitor-inductor, LCL filter resonance. The LCL filter is used to achieve the desired filtering effect with a minimum volume in this design. But the LCL resonance peak is a challenge to control. Look at the blue curve in the baud diagram. It's the frequency response of the LCL filter. It has a resonance peak at the resonant frequency, and the phase jumps by -180 degrees. When the third-order LCL network is included in the control loop, such as the grid current loop in grid-connected mode, there is the possibility of deterioration of power quality or system instability if it is not properly controlled. In order to stabilize the system, the resonance peak needs to be damped to below 0 dB. The most direct way to damp the resonance peak is to connect a resistor in series or in parallel in the LCL filter. In order to suppress the resonance while minimizing the impact on other frequency bands, adding a parallel resistor to the capacitor is a good choice. The red and yellow curve in the baud diagram are the filter frequency responses with different resistances. However, power loss on the resistor leads to reduced system efficiency. In order to solve the efficiency problem of connecting the passive damping resistor in parallel with filter capacitor, the filter capacitor current feedback control is added as the active damping in this design. The equivalent transformation of the control block diagram is shown here. Ignoring the control delay, the capacitor current feedback is equivalent to the passive suppressor, that adding parallel resistor to the capacitor. Now, let's take a look at the specific control strategies for grid-connected and standalone inverter modes respectively. In the grid-connected mode, The converter works as a current source because the power grid governs the voltage. Therefore, a single gridded connected current loop is adopted. The sensed grid current is the input, and the PWM duty is the output. Looking at the detailed implementation on the right side, a software phase-locked loop locks the grid phase. And then, the phase is multiplied with the peak current command to generate the current reference. To achieve error-free control, the quasi-PR compensator is used. In addition to the fundamental quasi-PR compensator, the harmonic compensators are also added to eliminate the corresponding harmonics. Besides, a PI compensator is added to improve the dynamic performance. Because the third-order LCL network is included in the grid current control loop, the capacitor current feedback is adopted to dampen LCL resonance peak. In addition, grid voltage distortion is also a challenge to grid-connected current control. The grid-connected current compensator mentioned above only covers the main harmonics. To cover more harmonics at the same time without affecting the grid-connected current loop gain, the grid voltage feed-forward is added. It includes three terms: proportional, first differential, and second differential. Next, let's take a look at the control strategy in standalone inverter mode. In this mode, the converter works as a voltage source, where the filter capacitor voltage is controlled. The voltage outer loop regulates the output voltage, and the inner current loop improves dynamic performance. Because the filter capacitor voltage is selected as the inverter output to be controlled, the third-order LCL network is not included in the control loop. There is no resonance suppression requirement here. Looking at the detailed implementation on the right side, the light blue box is the voltage loop. The sinusoidal reference voltage is generated by calling the NXP RTC-ESL library function. To achieve error-free control, the fundamental quasi-PR compensator is used, and the harmonic compensators are also added to reduce the THD. The orange box is the current loop. The output voltage feed-forward decouples the voltage outer loop and the current inner loop, makes the model simple. In the output voltage feed-forward, the reference voltage is actually used to suppress the effects of voltage jitter and improve dynamic performance. Next, we will talk about the hardware design. Here, we see the main power circuit of this design. It is a HERIC topology, followed by an LCL filter and the grid load connection switches. However, in current solution, only the 4-switch full bridge is used for function development. The two insulated gate bipolar transistors, IGBTs, in the middle of the two sub-bridges are disabled all the time. In this slide, we will go through the LCL filter design considerations. For the converter side inductor, it's calculated according to the maximum allowable inductor current ripple. Based on the calculation result, two standard inductors L20120-4162 MHF are used in this design. The total inductance value is 3.268 millihenry. When choosing the filter capacitor, considering that this design needs to be compatible with both the grid-connected and standalone inverter modes, the capacitance value is selected based on the reactive power it introduces. Based on the calculation result, a 2.2 microfarad electromagnetic interference EMI suppression capacitor is used. The cutoff frequency of the converter side inductor and the filter capacitor is about 1896 Hz, which is approximately 1/10 of the 20 kHz switching frequency, meeting the control requirements. For the grid side inductor, we need to pay attention to both the filtering and system stability requirements. Next, let's look at some software implementation details in this design. For multi-mode converters, The specific operating modes can be determined based on the grid and DC side conditions, or the instructions provided. In this design, due to the limitations of the test conditions, remote control based on free master is used to simulate mode selection and switching. This design supports 3 operating modes: PFC mode, grid-connected inverter mode, and standalone inverter mode. In this slide, the selection and switching logic between the PFC and inverter modes are presented. 2 variables are defined in the software. One represents the work mode command, the other one represents the current work mode. After reset, both variables are reset to invalid 0. The converter is idle and waiting for the valid work mode command. After a valid work mode command is detected, current work mode variable will be assigned to the value of the work mode command in the beginning. Then the converter starts to operate in the set mode. During the operation of the converter, if a valid change between PFC and inverter mode is detected in work mode command, the converter stops immediately because we need to reconfigure the experimental equipment. After the experimental equipment is reconfigured, enable the converter, and the converter will operate in the new mode. When the inverter mode is selected in the previous energy flow direction selection, we also need to determine whether to connect to the grid in this design. For the inverter mode selection, 2 variables are also defined here. One represents the mode command, and the other one represents the current work mode. After a valid inverter mode command is detected, current inverter mode variable will be assigned to the value of the inverter mode command in the beginning, and the converter starts to operate in the set mode. During the operation of the converter, if a valid change between grid-connected and standalone inverter mode is detected in the inverter mode command, the converter will continue to operate without interruption in this design, but a specific switching process must be followed to ensure system safety. Here, we can see the detailed switching process between the 2 inverter modes. When the converter needs to switch from grid-connected inverter mode to the standalone inverter mode, the grid-connected switch drivers are immediately turned off. However, due to the characteristic of TRIAC, the connection remains on until the current reaches 0. So, the converter is kept in grid-connected inverter mode before the grid current reaches 0, and then switched to standalone inverter mode control after the grid current reaches 0. When the converter needs to switch from standalone inverter mode to the grid-connected inverter mode, the grid voltage detection and judgment are performed first. After confirming that the grid voltage is normal, the inverter output voltage and grid voltage synchronization logic must be performed. For inverters compatible with grid-connected and standalone modes, there may be some load connected to the inverter output, so the inverter output voltage cannot be changed suddenly. For unsynchronized inverter output voltage and power grid voltage, if the grid-connected switches are suddenly closed, the huge voltage difference may cause serious consequence. So, the grid-connected switches can only be closed, and the control can be switched to grid-connected control after ensuring that the power grid voltage and the inverter output voltage are synchronized. Now, let's discuss in detail the specific implementation of pre-synchronization of the inverter output voltage and power grid voltage. Fast and stable pre-synchronization is a challenge. The amplitude can be matched easily by adjusting the inverter reference voltage amplitude according to current power grid voltage. To match the phase, the inverter output frequency needs to be increased or decreased. The phase synchronization implementation block diagram of this design is shown in the lower left corner. The software phase-locked loop calculates the phase of the power grid, and the inverter output reference phase is used directly as the inverter output voltage phase. To minimize the synchronization time, the correct frequency adjustment direction should be determined based on the current phase difference. The basic principle of frequency adjustment is shown in the lower right corner. When the phase difference is greater than 0 and less than pi, the power grid voltage leads the inverter output voltage. Increasing the inverter reference voltage frequency will achieve synchronization faster. Otherwise, decrease the inverter reference voltage frequency. Besides, the frequency change is limited to 1 Hz to meet the load requirements. Another point to be noted is that when the phase difference is around pi, the frequency change may jitter between 1 and -1 due to some measurement error, which will slow down the synchronization speed and may even cause synchronization failure. So, a hysteresis is added to avoid this issue. In the software, the inverter output reference voltage frequency is updated once per cycle to ensure the synchronization speed is accelerated while meeting the load requirements. The phase difference is obtained at the zero crossing point of the power grid voltage from negative to positive, and the desired reference voltage frequency is calculated based on this difference. Then the inverter reference voltage frequency is updated at its subsequent negative to positive zero crossing point. When the phase difference equals 0 or 2 pi, it means that the power grid voltage and the inverter output voltage are in phase, and the frequency change equals 0. Under this condition, the two voltages stay in phase after the phase match is obtained. Then, mode switching can be performed. Here we see the state machine of this design. All the operation modes share the same main state machine, and the code to be used is determined by current work mode variables. There are 4 states in total according to the converter status. After reset, the state machine always stops in init state, and it starts executing after detecting a valid work mode command. In the init state, all variables are initialized. After that, the state machine goes to the stop state. In the stop state, the converter is stopped and it waits for all startup conditions to be met. After all the startup conditions are met, the state machine enters the run state. In the run state, the converter operates in the set mode. Free master-based remote start and stop control is implemented in this design. In any of the above modes, when a fault is detected, the state machine enters the fault state. After the faults disappear, the state machine goes back to the init state to restart the converter. Next, let's look at the control timing. The timing of the real-time control system is interrupt-driven. To simplify peripheral operations during mode switching, the same interrupts, ADC, trigger signal, and sampling slot are used in all modes in this design. The Fast Control Interrupt Service Routine, ISR, is triggered by PWMA submodule 0 value 5, compare match with higher priority, and executed at the rate of 20 kHz. The frequency is consistent with the switching frequency, that is, it is performed once per switching cycle. All control loops in the inverter mode and the current loop in the PFC mode are handled in this ISR. The slow control ISR is executed at fixed rate of 2000 Hz using PIT0 ISR with lower priority. It is used to handle the voltage loop in PFC mode, so it is only enabled in the PFC mode. In addition to the above two control ISRs, there is also a protection interrupt triggered by PWMA fault 0 and fault 1, which are connected to hardware current protection detection outputs. Thanks to the automatic fault protection and clearing functions of the eFlex PWM module, we can easily implement cycle-by-cycle current limitation. And, combined with the interrupt count, the continuous overcurrent time can be recorded to determine further actions. It's useful in standalone inverter mode for non-linear load. The choice of a DC triggering moment is also very important for timing control and control requirements. To sample the average current, ADC trigger is generated by PWMA submodule 0, value 0 compare match, which is at the midpoint of the high-frequency switching. Looking at the timing diagram, the fast control ISR and the ADC sampling are triggered almost simultaneously in this design. So, the sampling value may not be ready at the interrupt start time. In order to make full use of CPU resources, code which don't need real-time ADC results are executed first, leaving more time for slow control, ISR, and background loop. Here, we see the fault protections that's supported in this design. The hardware protection includes inductor overcurrent and DC bus overvoltage protection, which is purely hardware-based and completely implemented by DSC internal peripherals. Look at the peripheral connection diagram on the right side. High-speed comparators are utilized for fault detection, and the built-in 8-bit DAC sets the fault threshold. The output of the comparators is connected to the PWM modules as the fault signal inputs, so that the drive signals can be quickly turned off when a fault occurs. For software protection items, some are related to the mode. For example, the grid voltage is not required in the standalone inverter mode, so its related protections are also not required in this mode. Last one, I want to show you this design in action. Some experimental results and waveforms are presented. Here are the efficiency and power factor of the design in AC to DC mode under both high-line and low-line conditions. The peak efficiency is almost 96% under high-line condition. This data is calculated based on AC source and electronic load display. The actual efficiency should be higher than this value, and the power factor is higher than 0.99 over the full load range under both high-line and low-line conditions. Here is the standard startup waveform in AC to DC mode. In this waveform, the green line is the input current and the light blue line is the DC bus voltage. The whole process is divided into 3 stages. In the first stage, DC bus voltage is pre-charged to near the peak value of the input voltage through TRIAC conduction angle control. You can see the input current is well controlled. In the second stage, DC bus voltage is soft-started to the desired voltage quickly. Then the DC bus voltage control enters the normal control mode. Here, because the load is light, the converter works in the burst mode. In this slide, you can see the steady-state waveforms in AC to DC mode. Under different input and load conditions, the input current is always in phase with the input voltage with small distortion. Here is the dynamic performance of this design in AC to DC mode. When the load changes from 0 to full load, the converter goes from the burst mode to the normal mode immediately with small voltage drop in both high-line and low-line conditions. When the load changes from full load to 0, the converter goes to the burst mode immediately with small voltage surge. The input voltage drop detection and fast recovery functions are also implemented in this design. This picture shows the experimental waveform of a sudden drop in the input voltage for 1 cycle. When the voltage drop is detected, the converter stops working. When the input voltage is detected to be restored before the DC bus voltage drops to the minimum allowable value, the converter immediately enters the normal operation mode and quickly charges the DC bus voltage to the required value. Next, let's look at the experimental results in DC to AC mode. Here, you can see the efficiency and the total harmonic distortion, THD, of the design under both high-line and low-line conditions. The peak efficiency is about 95% under high-line condition. This data is calculated based on DC source and electronic load display. The actual efficiency should be higher than this value. and the auxiliary power and the TRIAC conduction loss are all included in the overall power loss. The THD is below 3% with linear load over the full load range. Here are the steady-state waveforms of the converter in standalone inverter mode with a linear load. The output voltage and current are showed here. You can see the output voltage remains smooth and stable under different load. Here is the dynamic performance of the converter in standalone inverter mode with a linear load. When the load changes from 0 to full load, you can see the output voltage remains smooth and stable without distortion. In this slide, the experiment result of the converter in standalone inverter mode with a nonlinear load is presented. This experiment is based on high line and about full load condition. Look at the rose-red line in the waveform. It's the inverter output voltage. You can see that it remains smooth and stable. Here are the steady-state waveforms of the converter in grid-connected inverter mode. In the waveform, the green line is the grid-connected current and the blue line is the power grid voltage. Due to the driving characteristic of the TRIAC, there is a small platform when the current passes through 0. But overall, the grid-connected current is in phase with the power grid voltage, and the harmonic suppression effect is obvious. Finally, here are the experimental waveforms of switching between the grid-connected and standalone inverter modes. In the waveform, the blue line is the power grid voltage. The rose-red line is the inverter output voltage, and the green line is the output current. Looking at the waveform on the left, the actual switching point from grid-connected inverter mode to standalone inverter mode occurs when the current crosses 0. Subsequently, the standalone inverter maintains the current frequency and amplitude output. The right side is the switching waveform from standalone inverter mode to grid-connected inverter mode. You can see the inverter output voltage and power grid voltage are originally not synchronized, and the phase difference between them is gradually reduced through control. When the inverter output voltage and power grid voltage are fully matched, the working mode is switched at the voltage 0 point without any surge. That's all for this presentation. Thank you very much for attention.